Good morning, everyone. This is G. NARSIMHULU, Associate Professor, St. Peter's Engineering College, Hyderabad. Today we have the video lecture on Analog Electronics Introduction. This course was included in second year for SEM or 18 regulation under JNTU Hyderabad affiliated colleges and autonomous colleges. Let us go to that. What are the topics are there in this analog electronics? Here in this analog electronics, we have the different topics: diode circuits and MOSFET circuits, multi-stage and power amplifiers, feedback amplifier, and operational amplifiers. What are the core objective of the analog electronics? Means here we have to be introduced that components like new components in the electronic devices as per syllabus, that diodes and bipolar junction transistors and field effect transistors and their switching characteristics and applications, and how the high frequency analysis of the transistor is going to be takes place. It means that what is the difference between low frequency analysis and high frequency analysis of transistor, and we have to be uh, need to discuss about various types of basic and feedback amplifier circuits such as small signal, cascade, and large signal and tuned amplifiers, and also need to introduce the basic building blocks of the linear integrated circuits, which is very basic course after finishing this analog basic fundamentals, and to introduce the concept of waveform generators and introduce some special function ICs. Now, what are the course outcomes? What you gain after finishing this entire course? That we can be defined in terms of the course outcomes. The end of the course, the student will demonstrate the ability. He can know that one, he or she can know the characteristic and utilization of the various components, like that one diode and bipolar junction transistors and field effect transistors, integrated circuits and their applications even, and understanding the basic biasing techniques of the transistors, and we can able to analyze the various rectifiers, which is one of the application of the diode and small signal amplifier circuits even, and is able to design the sinusoidal and non-sinusoidal oscillators. It means we can be design the circuits by using the help of a passive and active components. We have to be come to know about this one, passive and active components, in upcoming classes, and it can also thorough understanding this functioning of the operational amplifiers, and how to design the operational amplifiers in the linear integrated circuits. Now let us move to the first topic, that is diode circuits. It comes under unit 1. Yeah, first I want to be introduce that entire course, chapter 1 to chapter 5. Then again we'll move to the diode courses. Here in the chapter 1 we have the diode circuits. In this diode circuits, we have to be discuss about what is the diode and what are the different materials. Depends upon the conductivity property of the materials, how we are going to be classify them. Like that one, conductor, insulator, and semiconductor. Then how the diode circuits are going to be defined, what is the definition, and um, current and voltage characteristics of that, and we have to be discuss about that, what are the basic applications of the diode, like that one, off wave rectifier and full wave rectifier, which are going to be used to converting AC to DC, and how we can be design the clamping and clipping circuits by using the diode, and also need to know about this basic fundamental theory about the bipolar junction transistors and their configurations, like that one, common base and common emitter, common collector configurations. Configuration in the sense how you are going to be connecting the circuit and how you are going to be biasing the circuit according to the application requirement. These things are going to be discussing in the diode circuits. and also need to know about this one load line analysis of the transistor. And we have to understand that one small signal equivalent circuit of the transistor, and we have to understand that one how the small signal analysis of the transistor in the different three configurations. Then we have to move to the chapter 2. It includes that MOSFET. There we have to be discuss about this one. What is the difference between the BJT and MOSFET? What the advancement is there in the MOSFET? Okay, why they introduce another field effect transistor is already it was there BJT. What the advantages MOSFET over the BJT? These things we are going to be discussed, and we have to be discuss about the constructional details and current and voltage characteristics and how we can be use this MOSFET as a switch. And we can also know about this one small signal equivalent circuit I to determine and do the some derivation part regarding gain calculation, input and output impedances, okay, and high frequency equivalence analysis. All these things we have to be discussing MOSFET. Then in chapter 3 uh, we will going to discuss about multi-stage and power amplifier. Why we need a multi-stage amplifier? Generally, the CE configuration of the transistor is using as an amplifier application, but even though if you take that one, it's a simple single stage BJT in the CE configuration, which is not providing that adequate amount of the gain requirement for the application. So that when we have to move to the multi-stage amplifier for the purpose of to acquire the adequate amount of gain. And if you have the multi-stage amplifier, we can have the another problem eventually, because multi-stage amplifier is only concentrating on this gain improvement, but your bandwidth is going to be decreased. So how it is going to be decreased? What are the impacts of multi-stage amplifier to define the bandwidth? All these things are going to be discussed, and how you can be connect the many number of CE configuration BJT transistors to configure like a multi-stage amplifier. What are the different techniques, like that one direct coupled and RC coupled? Yeah, meaning of direct coupled means direct connection. RC coupled means we have the RC components which are going to be taking as a coupling element between the two succeeding stages to define the multi-stage amplifiers. And what is a differential amplifier? Okay, this is also very important. Yeah, BJT can be used as amplifier, MOSFET is used as amplifier, multi-stage amplifier can be used as an amplifier, gain improvement. Again, why the new term it is coming, differential amplifier? These things are going to be discussed. And what is a power amplifier? Okay, here differential amplifier, multi-stage amplifier, MOSFET, and BJT amplifier. These are all small signal amplifiers. It means that it's going to be amplify the small voltages. What is a power amplifier? What is the difference between power amplifier and small signal amplifiers? What are the classifications comes under power amplifier? Like that one, class A, class B, class C, class AB. Some other extensive versions of this power amplifiers also there. Next, we have the feedback amplifier. In the feedback amplifier, what happened? Here, how the feedback is going to be taking place means that how you are going to be take the sample of output and mixing with the input, and what is the purpose of that feedback, and what the advantage you can be achieved by having the feedback. Okay, here we have the introduction of the types of feedbacks, that that one positive feedback and negative feedback, where we can utilize this positive feedback and negative feedback. Okay, what are the effects of feedback and amplifier characteristics, and these all things are going to be discussed. Generally, the classification of the feedback amplifiers, like that one, voltage series, voltage shunt, current series, current shunt feedback configurations are there. And there we have to move to these oscillators, like that one oscillator is a positive feedback circuitry which is going to be used to generate that one waveform. It is like that one signal generators. Okay, Here it can be generate different signals, and we have the different variety of circuits, okay, by configuring the different components, okay, like that one, what are the conditions need to be satisfied to get the full oscillation, like that one 360 degrees oscillation. Yeah, under this we have the different types of oscillators, like that one RC phase shift oscillator, Wien bridge oscillator, LC type oscillator, and these are Hartley oscillator, Colpitts oscillator. These things are going to be discussed. And final chapter is the fifth, that is operational amplifier. There we have to be introduced that one differential amplifier, and it is going to be basic building block of operational amplifier. What is the building block of the operational amplifier, how you are going to be connecting different blocks in the operational amplifier, why this operational amplifier is replaced with all the BJTs, and what the advantage you can be achieved, okay, how you can be achieve that advantage, what is the major circuit modification, okay, and what are the ideal characteristics of the operational amplifier, equivalent circuit of the operational amplifier, what are the DC characteristics and AC characteristics, and configurations of the operational amplifiers, like inverting configuration, non-inverting configuration, differential configuration, and what are the advantages, like that one again, clippers, clampers, integrators, waveform generators, triangular wave generators, spiral wave generator, multi-vibrators, okay, precision diode, all these are including this operational amplifier. This is the basic introduction of all the chapters of analog electronics. Now let us move to the chapter 1 introduction, that subheaded, like that one is the diode circuits. Okay, before going to be discuss about that one diode circuits, what are the basic things to construct a diode circuit? In the diode circuits, we have the topics like p-n junction diode and input current and voltage characteristics of the diode. These two topics today we are going to be covered in this video. Generally, materials are classified based on different considerations. But in this analog electronics, we are going to be classifying the materials depends upon the electrical property and conductivity of that material. So, like that one, based on the conductivity, we can be classify the materials like conductors, semiconductors, and insulators. What the difference is there? Yeah, the difference is forbidden energy band gap. Here we have the valency band. For every atom of the material is going to be having the valency band and conduction band, and we have the forbidden gap in between the valency band and conduction band. This forbidden band gap only going to be defined that one, what type of material you have chosen. For the insulators, we can understand that one forbidden energy gap is very high. Here it is equivalent to the 6 electron volt. Okay, what is the meaning of 6 electron volt? 1 electron volt means how much amount of force you needed to move the 1 electron. That you can be call it as a electron volt. Here, electron is having the negative polarity. To move that electron, how much amount of voltage you are going to be applying, okay, to move that electron, that you can be call it as a electron volt. So if forbidden gap is equal to the 6 electron volts between the valency band and conduction band, then you can be say that material called an insulator. And for the semiconductor material, yeah, it is lesser than the 6 electron volts. It is about the 1 electron volt. This one is wrong. It is 1.1 electron volt or less than 1.1 electron volt. Depends upon the what the semiconductor material you have chosen. One more point we have to discuss about this insulator. Here, when you have the gap is more between the valency band and conduction band, that we cannot be have the possibility to move the free electrons and free holes from valency band to conduction band, so that one these are purely insulated. The electron movement is not going to be taking place, that there is no current passing possibility through this material, that you can be called as a insulator. In the semiconductor material, which is having the energy band gap is equal to the 1.1 electron volt or less than 1.1 electron volt, it is depends upon the what type of semiconductor material you have chosen. What is the meaning of semiconductor material? This semiconductor material is behaves like in between conductor and insulator, like here sometimes it will be acting like a conductor, sometimes it is acting like an insulator, depends upon the at what temperature it is working, like that. Yeah, for the conductor, the forbidden energy gap is not there. It is going to be having the overlapping the valency band and conduction band. So you can be see this one. Next, let us go to the in details about the conductors. A conductor is a material which supports a generous flow of charge. Here is the charge in the sense it may be positive charge or a negative charge. Positive charge means holes having the positive charge, electrons having the negative charge. These charge carriers are going to be flow when you apply the voltage across the terminals. That you can be called it as a conductor, like the examples of these conductors like copper, aluminum, silver and gold. The resistivity of the conductor in order of 10 to the power of minus 4 and 10 to the power of minus 6 ohm per centimeter. This one is the resistivity. Resistivity you can be defined in terms of the formula. Rho is equal R is equal to rho L by A. R is the resistance of that material, is equal to the rho L by A. Rho in the sense the resistivity of that material. What is the L is length of that material, A is the cross sectional area of that material. That resistivity is very less for this conducting material. See that one 10 to the power of minus 4, it is very small value. 10 to the power of minus 6, very small value. Okay, right? That's what the unit of the resistivity is ohm centimeter. Insulators. An insulator, which is a material that offers very low level of conductivity when even applying the voltage. What are the examples of, like that one paper, mica, glass, quartz and kerosene. Okay, these are plastic, like some plastics. These are the insulators. The resistivity of this type of insulator, it is order of the 10 to the power of 10 and to the 10 to the power of 12. See that one in a conductor, it is very small, 10 to the power of minus 4, but here 10 to the power of 10, lot of resistivity is there. So that one it is not possible to make it to conduct. Okay, even if you apply the more and more amount of voltage, because the resistance are more. A semiconductor, which is a material as it conductivity lies between the insulator and conductor. The resistivity level in the range of 10 and 10 to the power of 4 ohm centimeter. The example for this semiconductor material, like silicon and germanium. Here types of semiconductor materials. Two types of semiconductor materials are there: intrinsic semiconductor and extrinsic semiconductor. The pure form of semiconductor, we can be called it as the intrinsic semiconductor, like that one germanium is a pure form of semiconductor, that is the intrinsic. Like that one silicon, it is a pure form of semiconductor, that you can be called as intrinsic semiconductor. Here the conduction possibility of intrinsic semiconductor is very less. Here it means that we have to be apply more and more voltage to make the free of electrons to move through the material. So it is very hard. Okay, so that one intrinsic semiconductor, pure semiconductors are not using in any applications. The conduction in intrinsic semiconductor, it can be achieved by thermal excitation and crystal defects, and we have to be give some heat for the semiconductor material, so that there is some possibility to have the free electrons, so you can have some current passing through that. Yeah, that is a intrinsic semiconductor. But electronic requirement is that we have to be make the free electron, we have to be make the free hole Okay, by applying a small voltage. Okay, small voltage, if you apply for the intrinsic semiconductor, it's highly impossible to carry the current through the material. So that we have to be go for the next type of semiconductor material, that is extrinsic semiconductor material. Here in this extrinsic semiconductor material, we can have the free electron by applying the even small voltage, so that we can have the conduction possibility to the material. Okay, that advantage you can be achieved by using this extrinsic semiconductor. Okay, this extrinsic semiconductor, when you call by adding some impurities to the intrinsic semiconductor, that material you can be called as the extrinsic semiconductor. Okay, here adding impurities in the sense we have the some material. Okay, we have the some extrinsic material, some impurities are going to be adding. That process of adding the impurities to the intrinsic semiconductor is called a doping. Okay, doping. So that the advantage of using the extrinsic semiconductor mean we can achieve the current conduction capability of intrinsic semiconductor can be increased significantly by adding small amount of impurity to the intrinsic semiconductor. What do you mean by diode? Diode is a junction of P and N. What is the meaning of P? It is a P-type semiconductor. What is the meaning of N? It is a N-type semiconductor. When do you say that P-type semiconductor and N-type semiconductor? We have, so far we know that one silicon semiconductor and germanium semiconductor. Silicon semiconductor can be converted as a P-type semiconductor. Silicon semiconductor material can be converted as a N-type semiconductor by doping, by adding some impurity to that one. You can be convert this pure silicon material to the P-type semiconductor, N-type semiconductor. Okay, here by making them to mix that P-type material and N-type material. Okay, the junction which is going to be forming in between P-type and N-type material, that junction you can be call it as a PN junction. In the p-type material we have the majority carriers are holes, and in l-type material we have the majority carriers are electrons. Let us move to that one. What is the p-type and n-type? After that again we'll come back to this one, how the diode will be functionally works, and what is the symbol of these things. Here we have to be know about that PN junction. Like already I told you know that when we have the p-type material and n-type material, which is going to be having the junction between that is the impurity material of P and the impurity material of N. It means that both are semi silicon or maybe germanium, but depends upon the what type of doping was happened over that material. This can be converted as a p-type and n-type, and when you make them to near to each other, and when you make them to attach each other, which is having mixing each other and forming the depletion layer, that layer you can be call it as a junction between the p and n-type material. And suppose two pieces are suitably treated to form p-n junction, there is a tendency for the free electrons from n-type to diffuse over the p side, and holes from the p-type to the diffuse over the n side. Here free electrons are there in the n-type which are going to be trying to diffuse to the p side, and we have the holes are there which are the free holes, majority carriers from the p-type which are trying to be diffused to the n-type. The process, this diffusing process, it means that majority carriers of n-type diffusing to the p-type and majority carriers of the p-type diffusing to the n-type, that process you can be call it as a diffusion process. The volts from the p side diffuse to the n side, and the electron from the n side diffuse to the p side. This gives the rise to diffusion current across the junction. As the free electrons moves across the junction from n type to p type, positive donor ions are uncovered, hence positive charge is built on the n side of junction. At the same time, the free electrons crosses the junction and uncover the negative acceptors. Positive charge carriers you can be called as a donors, and negative charge carriers you can be called as a acceptors. When the sufficient number of donor and acceptor ions are uncovered, further diffusion is prevented. This barrier is set up against further movement of charge carriers. This is called potential barrier or junction barrier. The potential barrier of the order of 1.1 volts to the 0.3 volts. Outside this barrier, on each side of the junction, the material is still neutral. Only inside the barrier there is a positive charges on N side and negative charges on P side. This is a region, you can be call it as a depletion region. The depletion region contains no free and mobile charge carriers but only fixed and immobile ions. Its width depends upon the doping level. Heavily doped means thin depletion layer. Lightly doped means thick depletion layer. PN junction can be basically work in two modes. A battery is connected to the diode, that is forward bias mode and reverse bias mode. When you say that one a diode in the forward bias, when positive terminal connected to the P region and negative terminal is connected to the N region of battery, then you can be call it as a forward bias mode. In reverse bias mode, the negative terminal of the battery connected to the P region and positive terminal of the battery is connected to the N region, then you can be call it as a reverse bias mode. This is PN junction forward bias. You see this one, positive terminal is connected to the P type and negative terminal is connected to the N type. Here free electrons are trying to diffuse towards the P type and free holes are going to be trying to diffuse towards the N type. This one you can be have this one positive ions and negative ions. Here electrons are going to be diffusing towards the N type, no free here, so that one negative ions and positive ions. It forces the majority charge carriers to move across the junction, decreasing the width of the depletion layer. This forward bias mechanism, the battery was connected according to this diagram, so that it is going to be making the narrowing the depletion region. When the depletion region will become narrow, the conduction possibility will become increased. See this one, we have the forward voltage, we have the forward current in milliamps, and here it is volts. Here voltage is goes on applying in increasing order. Then what happened? We have the decrement of the depletion region. So there is a possibility of increasing the free electron movement. So they're having the some current passing through the material. Here this one is the knee. It is a knee in the sense, knee voltage in the sense, this is a minimum voltage we have to be make it to apply between the P type and N type material as per this configuration, so that diode can start conducting. Until that you can be consider diode is not conducting, because it might be conducting but it is very small amount of conducting. It is just like not to be considered practically. Okay, thereafter once it is crossing the minimum voltage, that is a knee voltage, you can also call it as the threshold voltage, then diode will start conducting. So the current passing through the diode will become increased. Even after some time, if you though increasing the voltage, the diode conduction current is not going to be increased, because the free electrons of the given material is constant. After applying the maximum voltage, we cannot be having that one increment of the current. Same amount of current is there. Okay, but the speed of the current is going to be increased, so that one rate of change of charge carriers movement through the material, you can be understand that is the current is increased, but number of electrons which are available in that material is constant. When diode is connected in forward bias condition, a negative voltage is applied to the N-type material, positive voltage is applied to the P-type material. If this external voltage becomes greater than the value of the potential barrier, that is a 0.7 volts for silicon, 0.3 volts for germanium, the potential barrier opposition will be overcome and current will start conduct. Application of the forward bias voltage on the junction diode results in the depletion layer becoming very thin, which represents low impedance path through the junction, thereby allowing the high current to flow. At reverse bias, the battery will become reverse, positive is connected to the N type, negative terminal is connected to the P type. You see this one, This one is current, reverse current is going to be flowing through this one. We have the reverse voltage you are applying here from here to here. Here we are going to be applying here, slowly increasing the voltage. At one point, okay, the free electron and free volts are attracted towards the battery, hence the depletion layer will increase. Here depletion region will become increase. Okay, the depletion layer will become increased, so there is no possibility of the conduction, okay, of the diode when you apply the battery like this to form the reverse bias. But after some point, a reverse breakdown region will become, because here Ginor breakdown is there. After the Ginor breakdown, it's going to be conducting more and more with the with the negative polarity of the current. Here, when the diode is connected in the reverse bias condition, a positive voltage applied to the N-type material and negative voltage applied to the P-type material. The positive voltage applied to the N-type material attracts electrons towards the positive electrode and away from the junction, while the volts in the P-type end are also attracted away from the junction towards the negative electrode. The net result is the depletion layer grows wider due to lack of electrons and holes and presents at high impedance path, almost insulator. The result is that a high potential barrier is created, thus preventing current from flowing through the semiconductor material. Here VI characteristics of the p-n junction, this one. Here we have to take this one over the y-axis is the voltage, okay, that may be forward voltage and reverse bias voltage. Sorry, x-axis is the voltage, forward bias voltage, reverse bias voltage. Y-axis is the forward current and reverse current. Yeah, when the diode in forward bias, current increases exponentially with the voltage expect for small range close to the origin. When the diode in reverse bias, reverse current is constant and independent of the applied reverse bias. Turn on or cut in, or you can be called it as a threshold voltage in the forward bias diode. It is the voltage when the current increases appreciably from zero. It is roughly equal to the barrier potential difference. For germanium, cut-in voltage is equal to the 0.2 to 0.4 volts. For silicon, cut-in voltage 0.6 to 0.8 volts. It means this cut-in voltage or threshold voltage, turn-on voltage, this you can be understand, this is a minimum voltage we have to be applied in the forward bias of the diode to make it to conduct. Static resistance or DC resistance. The resistance of diode at particular operating point is called the DC or static resistance. The resistance of the diode at the operating point can be found simply by finding the corresponding level of the VD and ID. You can be understand what is the voltage at this point. It means that what the amount of voltage you apply, what is the amount of current passing through the diode. That you can be call it as a DC resistance. It means that resistance is not constant in the forward bias, because the resistance is going to be decreased while you are increasing the applied voltage. The static resistance means we have to be monitor the resistance of the diode at particular applied voltage. There you have to be find out the ID corresponding to the applied voltage VD, then you can take the formula or D is equal to VD divided by ID, then you can understand what is the static resistance of that diode at that particular applied voltage. The resistance may not be continued for after a long time when you are changing the input voltage. If you are not changing the input voltage, it's not the matter. The resistance is remains same. The lower current through the diode, the higher the DC resistance level. Dynamic resistance means the resistance is going to be changes with respect to the change of the applied voltage. As usually is going to be impacting over this how the conduction of the diode. It means that how the current passing through the diode is also going to be changed. The static resistance using DC input, it means input voltage, that VD is a DC, fixed voltage you apply. If the input is sinusoidal, the scenario will be changed. It means it is having the dynamic resistance and dynamic current. AC resistance is determined by a straight line drawn between the two intersections of the maximum and minimum value of the input voltages. There is a specific change in the current and voltage obtained. It can be determined using delta VD divided by delta ID. What is the delta VD? Small amount of change in applied input voltage. What is the delta ID? The corresponding change of the small amount of current in the diode for the change of small amount of input voltage VD. The ideal diode and the real characteristics even. Ideal diode is like this. It means that there is no conduction in the reverse bias. We have the fully conduction in forward bias. But practically it's not possible to having the conduction from initial stage of the applying voltage, that is VD is equal to 0 onwards. Practical is like this. The conduction will be takes place after cut-in voltage, turn-on voltage, threshold voltage in the forward bias. In the reverse bias, there is no current. Here ideal diode symbol is like this. Real diode symbol is also like this. Here we have the electrical circuit equivalent for the ideal diode is like this. A diode can be represented like a switch. In the forward bias, switch is closed. In the reverse bias, switch is open. But in the practical diode, we have the many things need to be included. Okay, we have the switch. We have the cut-in voltage battery, and we have the forward resistance even. That is the forward resistance of the diode. In the reverse bias, we have the open switch and battery and infinite resistance, because in open circuit having the infinite resistance. Diode equivalent circuit. Yeah, this one is forward bias equivalent circuit. You see this one, silicon diode. Okay, silicon diode mean it's not pure semiconductor material. Silicon is doped with p-type material and n-type material. They are going to be keeping side by side, having the impurity adding among them, so that it is going to be forming some junction that is called the PN junction, can be called as a silicon diode. Here we have the p-type and n-type. P-type is connected with the plus terminal and n-type is connected to the minus terminal. In between that one we have the R. You can be called it as a load resistor here. Here this one is representing of the diode with the resistance. Here resistance may be infinite. In the reverse bias, resistance will become 0 in the forward bias. That is the representation. We have the VR is a load resistor. Here we have the voltage, whatever you applied here, it is having ground. Okay, the current is going to be passing like this. Okay, this one is ID is nothing but diode current. VD is nothing but diode voltage. How much amount of voltage is going to be dropping across the diode? That is the minimum voltage 0.7 volts. This one is IR. It is a load resistor current. IR is equal to ID. Load line analysis. A load line drawn on the characteristics of the graph of the current versus voltage in non-linear device like a diode. The current shows the diode response, current versus diode current, while straight line shows the behavior of the linear part of the circuit. So we can be drawn the line between these two things, like VD is the diode current, I is the amount of current is passing through the diode, and we have the taking this one, what is the amount of current is passing through the diode when you are applying the static voltage, that is VDT. Okay, and R, what is the amount of resistance is there in the forward bias. What is the VDD? Okay, when we are drawing the line between these two things and current and voltage, that you can be called it as a load line. Here the relation between this, applying the static voltage Here you can be determined that how much amount of current is passing through this is equal to this VDD minus VD divided by R. The point of intersection given the actual current and voltage. Junction capacitance. We have the parasitical elements of the diode, like you know that one transition capacitance and diffusion capacitance. The transition capacitance, the amount of capacitance changed with increasing voltage is called the transition capacitance. It means that as input voltage is changing, so that one capacitance is also going to be changing. The transition capacitance also known as the depletion region capacitance. Okay, junction capacitance or barrier capacitance. As a depletion region was there formed between p-type and n-type material, that region itself is going to be acting like a capacitance. That capacitance you can be called as a transition capacitance. This depletion region size, it means that that dimension is going to be decreased or increased, depends upon the applied voltage. As you say that one, when the semiconductor material is acting like a conductor, the depletion region will become narrow. So the transition capacitance capacitor value is going to be decreased. When you have this one reversal bias operation, so that one depletion region will become wider, the transition capacitance will become increased. The change of the capacitance at the depletion region can be defined as a change in the electrical charge per change in the voltage, that is a dq by dv. So it is a transition capacitance. dq is a change in electric charge and dv is a change in voltage. Okay, it means that electrical charge, how much amount of electrical charge carriers are going to be moving, how much amount of voltage changing is takes place, depends upon that transition capacitance is going to be calculate. The transition capacitance can be mathematically written like you know that one CT epsilon A divided by omega. E is the epsilon is the permittivity of the semiconductor. It depends upon the what type of semiconductor you have chosen, like you know silicon having one type of permittivity, germanium having one type of permittivity, another having another type of permittivity, and the area of the plates p type and n type regions, and W is the width of the depletion region. Diffusion capacitance. This diffusion capacitance occurs in forward biased p-n junction diode. Diffusion capacitance also sometimes referred as a storage capacitance, denoted as a CD. The formula for a diffusion capacitance, CD is equal to dq by dv. Diffusion capacitance is going to be changed with the change of voltage. Applications of this diode. You can use diode like a switch, like a rectifier, clipper, clamper, reverse current protection circuit, like a fuser. You can also use this diode in logic gates and voltage multipliers. Many applications are there. PN diode switching times. Switching time mean what happened generally when we are applying the forward bias voltage. Previously it might be work in the reverse bias voltage, means according to understanding of the reverse bias voltage operation, we might thought that one diode was not conducting. Okay, let it be diode was not conducting. Once immediately if you changing the polarity of the applied voltage, applied battery terminal, then what happened? Diode need to be immediately into the conduct. But it's not possible. It takes some transition time. It was in the switching time, it was in the switch off time, switch off state, and it need to be come to the switching on state. In between that switch off state to the switch on time, switch on state, it takes some time to get back to the conduction possibility of that diode. That is going to be understanding switching times. And even if it is right now it is working in the conduction state, when you are changing the polarity and making it is working in the for reversed bias, it never goes back immediately into the reversed bias. It takes some time to goes back to the reversed bias. That is the understanding of the switching time. Here let me consider we have the input voltage. Here we have the input voltage. Let me it is having the forward voltage, diode will become forward bias. It is a reverse voltage. Here you see this one, minority carrier concentration, okay, and a diode current. Let us look at this one and this one. Your diode current, you see this one in the forward voltage, diode current is like this. In the reverse, diode current is going to be like this. It means that it's not going to be not to conduct. You see this one, once you changing the input voltage to the negative polarity, it means that in the reverse direction you can have the current largely in the diode with the negative polarity. But actually in the reverse bias, what happened, it need not to be conduct when you apply the reverse bias. It takes some time to go to the not to conduct. Okay, here we have the storage time, we have this transition time. In the transition time, it is going to be getting back to the not to conduct in reverse bias. That is it. You see here actually it was applied from year to year, and thereafter it is going to be extending, but in this time it is not showing not conducting state, it is in conduction state with the negative polarity current. Okay, and let me consider here this one, reverse recovery time, the time taken to having the uh, diode coming from the forward bias to the reverse bias, that is a reverse recovery time. You see this one is a forward voltage you applied, okay, forward voltage, and this one is a negative voltage you applied. Corresponding to that, what is the voltage across the diode and what is the voltage across the diode, here all these things. Okay, we have the technology related to switching time, that is storage time, the time period for which diode remains in the conduction state even in the reverse bias state is called the storage time. Transition time, the time elapsed in returning back to the state of non-conduction. The steady state reverse bias is called the transition time. Reverse recovery time, the time required for the diode to change from forward bias to the reverse bias is called the reverse recovery time. Forward recovery time, the time required for the diode to change from reverse bias to the forward bias is called the forward recovery time. This one is end of the class, which includes that one, what are the materials, how we can be classify the material depends upon the forbidden energy band gap, and what is a semiconductor, and what is a pure semiconductor, like you know that one intrinsic semiconductor, and how we can be make it as a extrinsic semiconductor, what is a p type material and n type material, okay, and what is the diode and how it is going to be work, what is the equivalent circuit, electrical equivalent circuit, and switching times and forward bias characteristics, reverse bias characteristics, all these things we discussed so far. Now it is end to this video, and in next video we'll cover the remaining topics, like it includes that rectifiers like half wave rectifier and full wave rectifier. Thank you one and all.